Hello, welcome back to another one of my video log recording sessions where I talk about genetic algorithms. Well, these days it's mainly on the on how to do genetic algorithms or evolution algorithms in a new fashion. I don't know if it's actually new, but chaotic genetic algorithm, and then after that onto chaotic dynamic genetic algorithm. So yeah, the date time right now is 2025 October 16th, and it has been 3 days or 4 days since the last recording, maybe. Yeah, 3 days. So, and in my last video, I finished off somewhere in the middle of something, because I felt that the video was getting too long, or was going to be too long, and it gets difficult for anyone, including me, to keep the focus, not lose the attention or focus when the video is more than 90 minutes long. So I had to end it there so that I can think more about what I'm going to cover in this video, which I did to some degree. And yeah, so today, or rather tonight, since so the I talked about the date, but the time is 46 past midnight. So I should say tonight. So tonight I am going to cover the number of data points and the time it takes for an iteration to run, depending on the hyperparameters. So and yeah, before I go into any of these, I need to explain one concept. So let's get into it. So the first thing, or the order in which these are done doesn't really matter, but the first thing is data point counts, or the number of data points during from or during an iteration, and the second one is time taken, the time it takes. And these are not the same as give me a good color, maybe this. Yeah, this looks good. So these two things are not the same as it's so hard to draw a straight line. These two things are not the same as number of generations. They are similar, but they're not the same, because before the chaotic version of genetic algorithms, when everything was when everything was kind of not chaotic, so I'm referring to dynamic and also the vanilla versions, right? Is it 2 L's or 1 L? I keep on forgetting. It is 2 L's. Nice. I didn't forget. Or I thought I forgot, but I didn't forget. But anyway, with these two things, because everything was centralized, or because every entity was included in a for loop that goes on for the given number of generations. Yeah. So for example, if it's 1,000 generations, this would continue for 1,000 times, and the metrics or the summed utility values of each and every entity, individual sums and world summed, would be recorded 1,000 times. So everything is centralized and linear, because it's easy to see the progress of the entities in a collective manner, and the progress of every entity on an individual basis. So that's easy. But now, some time ago, when I started this series, this new chapter about the chaotic way of doing things, I mentioned that the flow of time has to be different, or because it is different, and because it is different, the concept of time, and therefore time steps, has to be different. And this led to me changing the word generation to generation to blip, and within every blip it's made of sand grains, exactly like an hourglass metaphor. It is an hourglass metaphor. It is not exactly like, it is an hourglass metaphor. So blips and sand grains. Now, a sand grain is what an entity uses or consumes for an entity event or action. And a blip is made of let's say k number of sand grains. So each time a new blip starts, it is filled or refilled with a certain amount of sand grains, and usually this amount is it started with 2 times current population, and then there was a time when it was 3 times current population, 6 times current population, and there was a time when it was adaptive in such a way that it would, this number, the sand grain multiplier, I call these the sand grain multiplier, sand G multiplier. When there was a time when this was 2, fixed at 2, constant, and then it was 3, and then it was 6, and then there was a time when the sand grain multiplier would just increase as the number of items or number of genes increased, and there was a time when it would also decrease. So these two were adaptive. Okay, yeah, and the whole purpose of adjusting the sand grain multiplier, and therefore adjusting the number of sand grains, and therefore adjusting the number of entity events that entities could do per blip, which as a result would determine how long an iteration is. Iteration as in just one run. So all these are related. Of course, I could just increase the number of blips. For example, if I started with 100, and had I wanted to give the entities more time to do their things, I could have increased it to 200, which I did, 300, 400, or 1000, doesn't matter. But I also wanted to delve in to this because I just wanted to know if changing the k, which is the sand grain multiplier, is different from just blindly increasing or decreasing the number of blips. Yeah, so that's how time works here, or that's how the concept of time changed, because the flow of time changed when I went from dynamic or vanilla to chaotic. So back to here, data point counts and time taken. So in this setting right here, again, if the total number of generations was set to 1000, I would have 1000 records of whatever I'm trying to record. But in the chaotic world of chaotic genetic algorithms, that's not the case, because well, mainly because I would start with blip 0, and not usually, I said it so that the first blip would only have a fixed constant number of sand grains. For example, let's set that at 10, or is it 20? Let's just put it at 20. And then all these entities, the stars are the entities. All these entities would just spur into existence. 1, 2, 3, 4, 5. I need another one. Yeah. And then each time they do either one of these three things, not either, one of these three things, mutate, learn, or procreate. And C or CH as in chill, but this one doesn't consume a sand grain. these three do. So each time an entity does one of these three things, it consumes a sand grain, of which there were 20 to begin with. So while the entities are doing their own things, yeah, the world, for in this case the world.bin, the world module world or whatever, let's just say world. The world is keeping a record of the summed utility values of these entities. So when it does that, the world could have the world could have its first entities dictionary, which is a way to keep the summed utility values of all these entities. And while it's still blip 0, while we're still at blip 0, because the sand grains have not been exhausted yet. And then another one, still at blip 0. And then finally, if we run out of sand grains, we have a new blip. We go into a new blip. And then if there were like 15, 3, 4, and 5 entities, of course some of them could have been struck out or got limited out, but I'm not going to care about that right now. If there were 15 entities at the point when the new blip was started, then we have, for example, 30 sand grains. If the sand grain multiplier is where is it? Is 2, for example. So we have 30, and then the recording goes on, another recording, and now because we have 30 sand grains, it could or could not take more time for this new blip to finish and move on to the next blip. So in this case there could be again, there could still be 2 records from blip 1, and then we move on to blip 2, in which there were only 18 entities. So now we have 18 entities, and so now we have 36 sand grains. And then, but in this case, this blip took, during this blip there were 4 records taken. So this is from 2, and then in the fourth blip, which is numbered 3, there could be 5 records. 3, 4, 5. In the next blip there could still be 4 blips. Get it? So this is how it goes. So even when the blip, the maximum number of blips is set to 100, with the way things are going in this way, I could probably end up with something like 400 data points, because each one of these dots is a data point, as in a entities dictionary. So I could end up with something around 400 data points, meaning 400, maybe 300, 400, at most 450. This is when the sand grain multiplier is at 2. I'll show this soon, but just this is like a spoiler. I'll get something like 300 to 450 data points, meaning entities dictionary or dictionaries. So and this was when I set the maximum number of blips to 100. And usually you would, well, usually more data points could mean a longer time for the iteration to finish, but we'll see about that correlation as we go through the plots. So data points and time taken, that's what we're going to look at in this session. Alright, so 15,000, okay, so this is what I used for the last in my last video. I'm just going to copy and paste this because I think it's going to be useful. Let's have a look at the okay, let's have a look at the first run. This is the first of the 5 runs that I actually need to that I'm actually using to compare, and this is for the data point counts for the 10 event ratios, 10 entity event ratios. And what you can see here is that, well, let me just bring up this one. If you remember this, this is for the max of heads, or maximum of maximum evers, max of max evers, and here I remember having said that it's all concave shaped, and the red lines meaning that this is when the true ceilings happened, these 3. But here there isn't exactly much of a pattern, rather. I mean, the pattern seems to be that there is no interesting pattern. I think that's a fair way of putting it. Because there we go. So here we go. I'm gonna use pink. No, it's not catchy. I'll use purple. This is for the data point counts, or the number of data points, or the number of entities dictionary. Dictionary. And they all seem to have this pattern of going slightly downwards, upwards and then downwards, slightly up and then going down, and whereas here it's all kind of a flat line. But if we have a look at the average of each of these, well, the averages of these groups, each of which are 10, and where each group is made up of 10 event ratios. The average, it seems to, well, the average seems to decrease, because we started at 383, 372, 358, 370. So, so this increased, and then this decreased, and then this decreased. Let's have a look at the next row. 362, 371, minus 363, and then here we have a plus. Okay. 387 plus minus, still a minus, but let's just put this at 0, because it's almost no difference at all. It's like 1 second. It's like, this decreased, increased, and then decreased. So it's almost as if there's no no strong correlation. 0, increased. Why does that look like a cross? Increased, still looks like a cross. Increased and increased. Increased, 0, increased. Okay. Okay, maybe there's no actual difference. There doesn't seem to be that much of a difference when the chill ratio is, well, amongst the entity event ratios, where the chill event ratio is fixed, where is fixed as in they're all the same. So in this image, it's like horizontally there does not seem to be much of a difference. Let's have a look vertically. Is there a difference? It's like no diff. So let's have a look if there is a difference vertically. 383 when chill ratio is 0. 362 is, well, it decreased. 387, it increased again. So hold on. 383 when it's at 0. 362 when chill ratio is at 10. 387 when it's at 20. 374 when it's at 30, so that was a minus, and 381 when it's at 40, so it's a plus. Okay. The second column, let's go. 372, 371, so it's a 0. 371 to 395, it's a plus. Chill ratio 20, from 10 to 20, from 20 to 30 it was 361 all the way from 395, so it's a minus. And then 361 to 380, it's a plus. Okay. 380 to 393, it's also a plus. Alright. Chill ratio at 0, 358, 363, so it's a plus. 363 to 374, it's a plus. 374 to 365, it's a minus. 365 to 384, it's a plus. 384 to 392, it's a plus. Last column. 370, 376, it's a plus. 376 to 373, it's a minus. 373 to 361, it's a minus. 387, it's a plus. And from 387 to 394, it's a plus. Okay. So, I don't think I could say that I mean, I'm not running any statistical testing here. I haven't done that yet, but it doesn't seem that there's much of a difference when it comes to data point counts. Although it's tempting to think so, but at least not now. At least not with what I'm. At least not with the way that I program things right now. Let's just have a look at just one more. That was data points. There we go. Three 363, 358, 352. So it's all decreasing in the first row. 345, 353, 344, 3453, 353. Okay, kind of decreased. 354, 355, 356, 353. Very consistent this time. 361, 367, 361, 367. Wow, really consistent. 389, 376, 369, 386. Kind of decreased. 392, 392. Wow, again. 377, 400. Okay, increased. Let's have a look vertically. 374, 353, 354, 361, 389, 392. No. No strong correlation. 363, 344, 355, 367, 376, 392. Okay. 358, 353, 356, 361, 369, 377. 400, 386, 367, 353, 353, 352. Yeah. I mean, it could be that I am testing in that the range that I'm testing within is too small for the data point counts and the data point counts to actually matter or show any difference. But it does seem that if or when the chill event ratio is high and the procreate event ratio is also high or higher, there will be more data points. But yeah, okay, enough of that. Let's just have a broad or wide look, very wider look at these patterns. They are similar, but it's almost as if there is no pattern. They do go up slightly. In the middle, which is usually where the true ceilings do happen, like when the chill ratio, when the mutate event ratio and the learn event ratio is well, when these two ratios are kind of equal or within that range where they could be considered somewhat close together, not when compared to these extreme values such as 1, 86 or 87 and 0. So but apart from that, there's almost no distinct pattern. So it is kind of a concave, but it's not that strong. The shapes aren't that distinct, except this one. This one is an anomaly. Maybe this one's also an anomaly. Maybe this one. Let's have a look at this. I'm not going to copy this to Paint. It's about the same. We see those shapes. This is when it was flat, as in the mentor selection. The weights were flat. The weights for the mentor selection were flat. So compared to this is when the weights for the mentor selection was ReLU or ReLU-like, and this is when it was flat. Seems that when it's flat, the concave shapes tend to manifest themselves a bit more, but not that much. I mean, slightly more maybe. But this is very interesting. Yeah. Another instance where it was flat. Oh yeah, this one, the first thing that I showed, which was flat. This was where the elite percentage was 10%. This is when it was 20%, and would you look at that? We have this. Huh. Well, the mentor selection weights are flat. I think it takes longer. Maybe, maybe not. Have a look at a random thing. 1 6 30. When it's flat, it takes slightly less time. Slightly less, maybe. I'm tempted to say it takes slightly shorter time. Yeah, definitely shorter. So when it's flat, it takes less time. I think I can say that. It is likely to take less time. Wow, look at that. 10-second difference. Although I know it's on average, but 10-second difference. Okay. What about this one? This is the last of the 5 iterations. Let's have a look at the very last one. Yeah, still shorter. Or not less time, fewer data points, which could lead to a shorter time needed. So let's have a look at that. This, this. So this. Oh my god! Why do I keep loading up the wrong stuff? So on the left here is for the first of the ReLU weights, and these are all in seconds. So this, for example, these 10 had on average had an average of 53.55 seconds to complete. The longest taking somewhere in between 70 and 80 seconds. So this is like 76 seconds. Whereas here it's 56. Huh. 47. No, flat. Making it flat, making the weights flat, takes longer time. However, it produces fewer data points. Odd. And if you just have a look at the general shape of these, they are, well, should I say the opposite of concave, as in convex? They're in these two cases it's kind of flat, but we do see a lot of these balls or convex or V-shaped, in this case even V-shaped plots, or an S here, another S somewhere here. I remember seeing, maybe not, like a W. So most of them become W's, except this is a very funny W. Sort of like a basin or a W, can I say. Time taken. No, not that. Sorry. So here we have this pretty flat plot, and then a very mild W, somewhat of a W, weird W. This is like an S, ish. W, 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 definitely a W, 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 and then we had an S here. So yeah, pretty convex, I think, is what you say. S here, W here, W here. And I'm talking about the time it takes for an iteration. Huh. However, here, quite obvious, if you think about it. One thing that is quite obvious if you think about it is that the higher the procreate event ratio, the longer it takes. It goes from 33 to 32.99, and then 39.52 to 35.7. Same here. So they do increase. The time it takes, the time taken increases as the procreate ratio increases, which is, fair, which makes sense, because a higher procreate event ratio means that there are more entities, and more entities means more things for the computer to be running, which slows down everything. So here it goes from 37 to 44. Yep, 53 from 44. Yeah. Another thing. Let's have a look here. Let's see if this is also true. 47 to 55.74. (36, 41, 40, 45, 31). This is an anomaly here. Uh, 36, 35, 34, 32, 39, 35. Yeah, so higher procreate event ratio means longer time, usually. Let's see if that's true. This is the average of 24 groups. Each group being made up of 10 runs on 10 different entity event ratios. So this is the maximum average. I loaded up the wrong thing again, didn't I? So data point counts. Yeah, 0, 10, 20, 30, 40, 50. So the data point count does somewhat increase as the by a small amount, does somewhat increase as the chill event ratio increases, but not substantially, as we can see here. But the time it takes for an iteration to be over, there we go, we do see an upward trend. And here the upward trend is also visible when we increase the procreate event ratio. So this here is 3, 4, 5, 6, and then down to 3, 4, 5, 6, 3, 4, 5, 6, 3, 4, 5, 6, 3, 4, 5, 6, 3, 4, 5, 6. But the effect that the procreate event ratio has on the time taken seems to have a bigger impact when the chill ratio is higher. When it's 0 or 10% or 20%, they don't really seem to, the procreate event ratio does not really seem to have an impact on increasing the time taken. But when it's above 30%, for example 40 and 50, it does increase the time taken. It does increase the time it takes, the time required to finish the run. Same here. Yep. Yep. And here we go. 18. Okay. So let's just have another look at when let's have a look at when the true ceilings were achieved, and then look at the data point counts and the time taken for these entity event ratios. I think that's fair, right? And since there are only 4 of them, I don't think it's going to take a long time. So the first is 31, 24, 5, 40, which is here, I think, since this is the first one. No. 31, 24, 5, 40. 31, 24, 5, 30, 40, which is this one right here. And then the next one is that, and 16, 31, and 3. Oops. 16, 31, and 3. This one. And here it's this one. And then from here, from the next one, it's 53, 43, and 4. "53, 43, and 4. There we go. Is that right? Yeah, that's right. And then we also go to the time taken to get these, which is what? Again, oops. 25, 20. Hmm. 25, 20. This one. And this one. 1, 2, 3, 4, 5. From here it was this one, wasn't it? 16, 31, 3. No, it's 11, 36. No, 16, 31, 3. Yep. Got that right. Let's see if I have that right. Just checking. And then 20, 25. And above that, yep, got that right. So, when it comes to data point counts, we do get a higher than average data point count when a true ceiling, or when more than one true ceiling is reached, or rather achieved. Not the highest, not necessarily the highest. Oh, in this case it was the highest. And here but time-wise it's shorter than average. So if there are a lot of data points, however, if the time it takes for the run to finish, to complete, is shorter, it means that we have more data points, but it takes shorter amounts of time, shorter duration. It means that there were a lot of entities, and therefore a lot more sand grains. A lot more sand grains means that a blip lasts longer. A blip is likely to last longer in terms of absolute time, which in our case is seconds. So more entities leads to more sand grains, which leads to which likely leads to longer blips. More entities, more sand grains, more longer blips, which leads to more data points. But yeah, more data points within a relatively similar amount of absolute time, which in our case is in seconds and minutes. Our time, or physical time. I know time is relative, but in our case time is still absolute. So anyway, however, that's not the case when we just have a lot of entities being produced, and which more entities. On the other side, or on the other hand, on the flip side, more entities mean more stress, more load for CPU, which means slower processing time, slower processes, which leads to longer time. So there's a trade-off. Because if we have more entities and therefore more sand grains, however, if this leads to potentially longer blips, or potentially longer blips because there are more resources, sand grains, in each blip for the entities to consume. However, if the entities are active enough, quote unquote, active enough to use up these sand grains, that blip can end more quickly, can be over. That particular blip can be over more quickly. However, if there are more entities, it means more load for the CPU, which is slower, which leads to slower processes, which leads to longer time. So it's all a very complex, complicated, well, it's all very complicated because all these factors don't nudge the results, nudge the data point counts, and nudge the time taken to be higher or lower, because they all have very they can have very opposite or contrasting effects. Of course, if I had a bigger capacity to compute, more compute power, maybe I can know more about it, and maybe also run these iterations 100 times or more to get a more exact estimate by averaging everything out. But so far it's by ReLU mentor selection, it's 4 out of 480. Is that right? Yeah, it was 3 out of 240, and then it was 1 out of 240, so that leads to 4 out of 480, so which is 100, yeah, which is 1 over 120. And when I do it flat, it was 0 out of 480 when the elite percentage was 20%, and it was also 0 out of 240 when the elite percentage was 10. So it's really hard to get the true ceiling when I only have 100 maximum population. Which gives me another idea. The idea that I should do, I should try pseudo chaos with only 100 population, and see if the true ceiling is achieved. Of course, it's not pseudo chaos and true chaos isn't the same, but because it's relatively quite easy. It's very easy to get the true ceiling when doing pseudo chaos. I've figured that out, and it takes a lot less time as well. Yeah, I should try that. I should try this to see, yeah, to actually be able to compare pseudo chaos and chaos. It's not that I need to really compare to know which is better. Pseudo chaos is better if I'm trying to just optimize towards a solution, but since that's not exactly what I'm doing, I don't really think I need to, but just out of curiosity, maybe I will. Before I finish, let's have a look at the entity distributions. Entity distributions when the true ceilings were achieved. I think that's a good place to end. 13, 24, 5, 40. Give me 13, 20, give me 13. What? No, it's 31. Why did I say 13? Could be really 31, 24, 5, 40. So here we have the first time the true ceiling was achieved, and the next one is what? Oops. Is this one 16, 31, 16, 31, 3 and 50. Yep. Let's have a look at the last one. Okay, fairly distributed. I think this is going to be more converged. Yeah, it is. Now, on the left is better distributed because of the lower, lower learn event ratio. And then you might say, wait, this is 31 and this is 24. 24 is higher than, well, MLP. 24 is lower than 31. That's true. And that's why on the right is more converged, or rather over converged, because the population in this case was 89 and we have 59 entities sitting at the true ceiling. And this started when? In total there were 421 data points. Ignore the part where it says add blip here. That's a mistake. I wasn't being too careful. I should have. So this is at data point 290. This is not, and this should not say blip. This is my. It's not a typo. It's just my mistake. Just a plain old mistake. So out of 421 data points, the state of overconvergence was first apparent at 304, whereas in this case convergence didn't happen until the very end, probably until the very end. So I don't know if let's have a look. I mean, this is also good, alright? Because until it converged, it was doing quite okay. No, it wasn't. Maybe it was. No, it wasn't. Okay. Show me the other one. 25, 25, 50. So, top is 28, well, true ceiling, achieved. Mode is 16, and population is 67. So, this is 16 entities. And right here, there's another one. Is it 4 entities? Yeah. 4 entities above, 4 entities at the true ceiling, right here. And when did this convergence happen? Near the very end. Out of 413 data points, the first time the true ceiling, well, and it was achieved was, these are just snapshots. I still have all the 413 or 400 something entities dictionaries, but these are just snapshots because I only made 30 of them per event run per entity event ratio, because I'm making 400 something plots for 240 ratios was going to be almost impossible, or it was just going to take too long. But anyway, here convergence happened towards the end. Yeah, I think I can say that. So not that well distributed, because comparing this, if you compare this to which one? Yeah, this. I would say this is a more healthy looking distribution. And even when I compare the left to the right one, yeah, having a longer tail, I don't think is that good, because it's too far away from the true ceiling, or from the center of mass, I guess I should say. Whereas here it's on the left, here it's too converged. This on the left should be kind of exactly before the entities converged to true ceiling, and then this happens. So within a span of 14 data points, this happened. From this, it went from this, the entity distribution went from this to this. So the entities converge to the true ceiling quite rapidly. which again confirms that if you give them a chance, give me a golden star. If you give them a chance to converge, it's like, come here. If you give them a chance to converge, the entities will just flock to this. We'll just take this opportunity and converge because of the learn event. Okay. So and 14 data points is what? So 100 blips, as you can see here, is usually somewhere between 3, no, at the lowest it's 350 to 450, at most 450, I think. No, for that I can just go here to find that out. Oh my god. Data points, give me this. Data points, 450, 400, 400. Oh no, this is per average. Data points, give me, there we go. The most is 430 or 420 ish. 450. See, we even get 450. So I think it's safe to say that it's where is that? There. So it is safe. I think it is safe to say that 100 blips would equal 300 to 450 data points. So that's about 3.5 to 4.5 data points per blip. So 14 data points is about what? 3 to 4 blips. So when the opportunity to converge, meaning when a true ceiling has presented itself, the entities will converge within 3 blips. Is that true? Let's find out. $65, 14. Yeah, this is the first one. Let's have a look here. This is when it over-converged. $290 and 304. Again, 14. I know it didn't. The true ceiling wasn't achieved here, but it happened during these 14 data points. So I think it's somewhat safe to say. Safe to guess that that's what happened. Let's see here. We still have 4 true ceilings, 4 entities sitting at the true ceiling. So right before, when did we get the top? It's like 384 and then 398. 14 again? Well, it could be 14 because of the way I split everything. But I think it is still safe to say that convergence to the true ceiling will happen in 3 blips, or about 3 blips. So if I were to give a range, it would be from 2 to 5 blips. Of course, this is supposing that the entity ratios given can produce true ceilings. By the way, this is the data point counts for all 240 event ratios, not grouped, just for individual event ratios. Yeah, and you can see why it's so hard to try to find a pattern here. See, everything just looks like noise. Which is why I felt compelled to average sections out to smooth these lines. Maximum errors. Yeah, we know this. Time taken. So data points stay relatively the same, whereas time taken does seem to increase as the chill event ratio increases, but not that much, not by a lot. So I think the next step for me is to first do the easy thing first. To do this, yeah, so to do this, the pseudo chaos, and then try to find out pseudo chaos with 100 entities max, and try to find out the chances of me finding getting true ceilings, achieving true ceilings. And the next thing to do for me would be to do all of this same thing, but do it in the, where is it? I didn't write it. Do it in the chaotic dynamic way. No, chaotic dynamic genetic algorithm way, and see if the findings of the takeaways are the same. Oops. Why did I enclose everything? Yep, I think that's what I should do. Alright, thanks for watching. I think that's it. Yeah. Bye.